Hello students, in this lecture we will discuss what will be the inverse of a subset of a group and will derive theorems based on uh, subgroup of a group to be a subgroup. So let us first of all define the inverse of a subset of group. Let H be a subset of a group G. Then the inverse of H is denoted by H inverse, which is equal to which is equal to the set of all H inverses such that H belongs to H. What is the binary combination operation? Binary combination is multiplication. Binary combination multiplication. If the binary combination is addition, then H, if H is a set of is a subgroup of G, if H is a subgroup of G, then H inverse will be the set of all minus H such that H belongs to H. H is a subset of a group G. This is under the binary coefficient addition and this is under the binary coefficient multiplication. Now theorems from this. If H is a subgroup of G, the group G, then H inverse equal to H. H inverse and H both set will be now uh, given is H is a subgroup of a group G. To prove is H inverse equal to H. That is H inverse is set of H and H is set of H inverse. First part is to show that H inverse is subset of H. Let H inverse is equal to, let us take H inverse belongs to H inverse. Definition of H inverse be any element where H belongs to H. Since H is a subgroup of G, therefore H inverse also belongs to H. Because in a subgroup, inverse of every element exists in that subgroup. So now, if H inverse belongs to H, we have implied H inverse belongs to H. We have shown that H inverse also belongs to H. Implies H inverse is subset of H for any element H. Second part is to show H is a subset of H inverse. So we'll take H belongs to, let us take H belongs to H. Any element of H. Since H is a subgroup of G, therefore H inverse also belongs to H. So H inverse belongs to H. Inverse of, you know, the inverse of element is element is the taking inverse of both sides. So H inverse of H also belongs to H inverse. Definition of H inverse. If H inverse belongs to H, then inverse of H inverse also belongs to H inverse. So inverse H inverse inverse of H is equal to H. We have taken H belongs to H and we have shown that H also belongs to H inverse, implies H is a subset of H inverse. In first and second, the first and the second, A and B, this both A and B implies H is equal to H inverse if H is subgroup of H. But the converse of this theorem is not possible. It's not true. That is, if H is subset of G such that H is equal to H, then H need not be subgroup. Converse of this theorem. We are supporting this with an example. Example is, let G be a subgroup. G be a group of square root of unity. So my friend, if you write down the composition table of 1 and minus 1, and internal is 1, inverse of 1 is 1, 1 minus 1 to 1 is equal to 1, closure property, and 1 into minus 1 is equal to holds true, actually holds true, inverse element, inverse of minus 1 is, inverse of minus 1 is minus 1, and inverse of 1 is 1, and composition table this is a group. It's a group, and the composition of multiplication. Multiplication, let H consist of single element minus 1. So minus 1, if it consists of this, is a subset of G. Okay, this is such a group. You can see this is a group. And so now you want to do. Now H inverse is equal to, what is H inverse? Inverse of minus 1 is minus 1. Minus 1 into minus 1 into minus 1 is equal to 1. So H inverse minus 1. So the set H inverse will be -1, is equal to H. H is one element, and inverse of -1 is 1. So -1 is equal to H. H is also -1. H inverse is -1. So because inverse of element is equal to 1. So you know 1 upon -1 into -1 into 1. But H is not a subgroup. H is not subgroup. Why? Because this H does not contain the identity. If one to 4 exam does not hold true, implies the subset of the group G is not set. So identity element does not exist, implies H is not a subgroup. And next term is a non-empty subset H of a group G is a subgroup of G if and only if H into H is equal to H. Then sorry. Then, if a non-empty subset H of a group G is a subgroup of G, then H into H is equal to H. Now, given H is a non-empty subset of G and G is equal. And what is H? H is a subgroup of G. Now, our aim is to prove H into H is equal to H. That is, what H into H is subset of H and H is equal to H. So, first part, H into H subset of H and H is subgroup of G. H, let us take H1 and H2 belongs to H. There are two elements such that H1 to H2 belongs to H into H. H is a subgroup, therefore H into H also belongs to H. What is about it? So we have this implies H into H equal to H into H. We have shown that because it's a subgroup H into H, H1 into H2 belongs to H. This implies H1 into H2, H1 H into H, H into H is a H into H is a subgroup of H. H is subgroup. Now second part, H is subset of H into H. Let H belongs to H, be an element of H, and H subgroup, therefore E also belongs to H. So H is equal to H into E. So H belongs to H, E belongs to definition product of two subsets. So H is equal to H into E belongs to H into H. This implies if H into H implies H belongs to H into H. Thus H belongs to H implies H into H belongs to H into H. So this implies H is equal to H into H. So A and B implies A and B implies A and B implies A and B implies H equal to H. It's a G, H equal to H. Again, the converse of this theorem is not true. Not true. If H is a non-empty subset of a group G, such that H into H is equal to H, then H need not be a subgroup. Again, the supporting example is this. Let H is H be a additive group of integers. Means H is a set of integers and the value of addition is a group. Let us take H the subset of all positive integers. All non-negative means all positive integers. Then H into H is H. If you take n two elements of H, they also belong to H. But H is not a subgroup. Why? Why it's not a subgroup? Because inverse element of none of the elements of H, none of the elements of H have an inverse element in H. So H is not a subgroup. One doesn't inverse element exist. So one of the examples does not hold true, implies H is not a subgroup G with the condition H is H. The next term is if H and K are any subsets of group G, then H K inverse is equal to K inverse H inverse. Reversal or group. Given it H is equal to subgroup. Proof is H K inverse is equal to K inverse H inverse. That is the proof is H K inverse subset of H K inverse H inverse, H and K inverse H inverse is a subset of H inverse. First part will prove it. Prove is H K inverse is a subset of K inverse H inverse. So let us take example any element belongs to this. H K inverse is equal to belongs to H K inverse. For all H belongs to H and K any element, we taken any element of H K inverse. Now H K inverse is equal to reversal order K inverse H inverse. So this belongs to first element to K, second belongs to K, first element to K inverse, second belongs to H inverse. Lies H K inverse belongs to H K inverse, and we have shown that K this also belongs to H K inverse belongs to K inverse H inverse. This implies H K inverse subset of K inverse H inverse. Now second part. K inverse H inverse is subset of H K inverse. So let's take an element from the left side. K inverse H inverse belongs to definition. Because of this definition. K inverse belongs to K inverse H inverse. Therefore, K inverse H inverse belongs to K inverse H inverse for all H K belongs to H K. Now K inverse H inverse reversal order is the because K inverse H inverse is equal to H K inverse is equal to H K inverse, which is the reversal order for the inverse. So where from this belong? It belongs to H belongs to H K inverse. So we have taken K inverse H belongs to K inverse H inverse and shown that K inverse H belongs to H K inverse. This implies K inverse H inverse is subset of H K inverse. So we implies if H and K are subsets of group G, then H K inverse is equal to K inverse H inverse. K inverse H inverse. The next one is if H and K are two subgroups of a group G, then HK is a subgroup of G if and only HK is equal to H. For any two non-empty subsets of a group G will be a RP then the product will be a subgroup. If H is a subgroup of G, then their product will be subgroup if the subgroups commute. Subgroups commute is HK equal to KH. Now, some necessary part given is H and K are subgroup of G and HP is a product HK subgroup G. Our aim is to show HK equal to KH. HK equal to KH. So, given HK subgroup, so HK is equal to like this. If H is equal to G, H is equal to H. Prove this term. If H is subgroup G, H is equal to H. So, HK, we are given HK subgroup G. So, HK is equal to H inverse. H inverse, reversal of H and K are they are subgroup, they are subsets. Reversal of whole 2, HK, H inverse H inverse. So, HK K inverse K inverse. So, our aim is to show, but HK H inverse H is equal to H subgroup G, H is equal to H, so K inverse equal to K, and H is equal to H. So, H is equal to H is equal to H. If H is subgroup, then and H is subgroup, then H is equal to H. Now, sufficient part is given HK as subgroup of group G and such that HK equal to H. Our aim is to show HK is subgroup G. That is to prove. What is to prove? HK subgroup G means we have to prove that H inverse is equal to H. H subgroup G, we have to prove the theorem. If H inverse is equal to H inverse H, we have to prove this theorem. So which here, just now. So we prove this theorem just now. So we'll prove it. We'll take a different search. You have to prove HK subgroup, you have to prove H inverse equal to H. So HK subgroup, HK inverse equal to H. So we'll take a different search. So and equal to HK to HK inverse. H and K subgroups. So HK subgroup there are subsets. So HK inverse equal to K inverse inverse. So this is equal to HK inverse equal to K inverse inverse. I should it down. HK K inverse equal to K K inverse H K K inverse H inverse K K inverse K is a subgroup of G. K K inverse is equal to K. Equal to K. Now again associative law. H K is equal to given. H K is equal to KH. Is equal to KH. Again associative. K into H K H inverse H is a proof. Therefore H inverse is equal to H. So is equal to H K inverse is equal to H K. Right hand side implies H is a H K subgroup. Now corollary based on this. Corollary based on this. If H and K are subgroups of an abelian group G, if H and K are subgroups of an abelian group G, then HK is a subgroup G. Proof is based on the previous theorem, corollary is a previous theorem. Since H and K are subgroups of a abelian group G, implies H and K are subgroups of abelian group G, implies HK equal to KH. Then sufficient condition of the above theorem show that if HK is equal to KH, then HK is a subgroup. Thank you.